All right, let's start by following up on various topics that we've talked about, and maybe we can emphasize some points about them a little more this time. Let's go back to some properties of the Fourier transform. So one of the properties we mentioned is that there's this linearity. And so I'm going to do an example of using linearity when computing a Fourier transform. Take, for example, a function that I'll just plot. Simple function like this. Value 1 here, value 2 there. Okay, so here's a simple function. If we want to compute the Fourier transform, of course, you could plug this into integrals, but we could use linearity and decompose it into a sum of rects. In fact, there's a couple of ways we might do that. So I'll do this example two different ways. And partly we're doing this just so we can practice using properties of the Fourier transform. You'll see that by doing it two different ways, we'll just get some more practice. All right, so one way is to say, and this first way is the easy way of the two. You can say it's one rect from -half to half, and another one from -1 to 1. You see that if we sum these together, that would give the original signal. Okay, so then by linearity, that would tell us that we could think of x of t. First of all, write this out by formula. It's rect of t over 2 plus rect of t. Okay, and that means that the Fourier transform is just the sum of the two Fourier transforms. Now we have to use the time scaling property for the first one. So that's going to be 2 sinc of 2f plus sinc of f. Okay, so quite simple. Now I'll do it another way, just to show that it can be done two ways. Also, it's going to be a slightly harder way, but it'll give us more practice again with calculating Fourier transforms. So we could decompose it this way. Notice that if we add, well, that's kind of crooked. If we add these two rects, then same thing happens. Add those together, you'll get back the original thing. Okay. So put a big or here. We could do it this way. X of t equals, now what's the formula for these? Well, you have to be careful. There's a time scaling from the original rect. The width here, rather than width 1, it's width 3 over 2. Okay. But then there's a shift. I'm going to apply the shift after the time scaling. So, in other words, scale it to width 3 over 2, and then, so that means it's going to be rect of 2/3 times t, but then I'm going to replace t with t minus its center. So let's say that first one is t plus, what's the center here? It's -1, it's -1/4 is the center. So t plus 1/4 minus a -1/4. Okay, so this is one way to decompose it. Now we can, again, let's apply our transform. Now notice what I did here was a scale, then shift. Remember that the order you do it is going to just determine, here, why is it a scale first and then a shift? Because if you work from the outside in, there's the time scaling first and then the shift second. Okay. If you wanted to do a shift and then a scale, that would be the same as just multiplying out this argument inside. Okay. So what does that mean for calculating the Fourier transform? Well, I use the two properties. So I say rect of t goes to sinc of f. Therefore, rect of 2/3 t goes to 3 over 2 sinc of 3 over 2 f. Now, one thing to keep in mind with that time scaling property, if f appeared multiple times on the right side, each one of them would have to be replaced with a 3 over 2f. Okay, so if for some reason you had like some other formula there with f appearing multiple times, replace each one. All right, and then finally, then rect of 2/3 t minus a fourth. Notice that this is exactly the above function. See, if I do it in these steps, it helps me keep track of what order I should do the shift in the scale, right? Because clearly this last one I'm writing is just the one above it with t replaced by t minus a quarter. That's a time shift. Oops, let's do plus just to match our term above. So that's going to be e to the I pi over 2 f times what we already had, 3 over 2 sinc 3 over 2 f. Okay, so those are the intermediate steps. Now let's just jump back to what we, from up here, we have, therefore, the Fourier transform of x. It's just going to be the sum of two things which we've just derived. It's going to be 3 over 2 e to the I pi over 2 f sinc 3 over 2 f plus this other one that has a negative there. Okay, so we're saying that's the Fourier transform. Two different ways to arrive at the same thing. But these aren't the same, right? This one is, we have two completely different formulas for the Fourier transform. So surprisingly, these are actually the same thing. This here and this here are the same. Of course, checking that they're the same takes a little bit of work. Now, you wouldn't have to, like if this were on the exam, for example, you wouldn't have to write it exactly the way, either way would be fine. But because we're practicing, let's just check that these are the same. All right. Of course, the key here is to do to use Euler. So I'm going to start with this one, the complicated looking one to the right. And let's just rewrite it. So first I'm not changing a thing here. But then let's say that equals, and now the sinc by definition is a sine of pi times the argument over pi times the argument. Okay, let's plug in the definition of sinc. And what we're going to get is the 3 over 2's cancel. So we get e to the I pi over 2 f sine of 3/2 pi f over pi f. All right. Now, if I didn't care to move quickly through the example, the way I would do this is I would expand sine out using Euler's identity as two exponentials. then the numerator here would just be a product of exponential functions. I'd multiply them out. They'd all simplify. I'd have 4 exponential terms, and I'd go combine them back with Euler's to get back to sines. Okay? But slightly less writing is we can just refer to a trig identity. We can say, notice, what is this? We have sine appearing twice here, so factor it out. We have an e to some imaginary exponent, e to the negative of that imaginary exponent. That's a cosine. We can recognize that as a cosine. So I put the 2 there from the cosine formula. So it's cosine of pi over 2 f times sine of 3 over 2 pi f in the numerator over pi f. Okay, so I used Euler's identity, turned them into trig functions, and here I'm going to say, oh, well, I know a trig identity. I know how to do a cosine times a sine, and when I do it, I'm going to get just sine of pi f plus sine of 2 pi f over pi f. And now I recognize that as the formula up here. Okay, so indeed they are the same. Let me just mention again why. Okay, here I used a trig identity. In real life, I hate to memorize trig identities. So I always just like to derive them using Euler. So if I were doing this myself and didn't want to have to look up a trig identity or remember it, I would not go through this step. I would just say, I would expand out sine as complex exponentials. You get 4 exponential terms here, and they'd match up, the exponents would match up into pairs. And that's how you get this one sine and another sine. Okay. Let's look at the derivative property. This we barely discussed in lecture, but you did have a problem in one of your problem sets that asked you to use this derivative property. So let's revisit this. It says that the derivative of x of t, if you take the Fourier transform of the derivative, you get I2 pi f times the Fourier transform of x. Okay? What this does is it means that the derivative simply amplifies higher frequencies. That's exactly what a derivative does. It also has some sort of phase. So what I'm saying by amplify is this. It's simply you're multiplying this function times the original spectrum, x of f. Okay? What is this function? Well, it's just linear in f. It has an I2 pi, but ignoring that, it's just linear in f. Higher frequencies get amplified more. Okay? We could also recognize that, well, this is a multiplication in the frequency domain. Therefore, it must be a convolution, or it must be a linear time invariant system. And indeed, derivatives are a linear time invariant. That's why in the frequency domain, all it's doing is multiplying by some function. Okay. Now, you could from this infer that integration is the opposite. Okay, so for example, if you say integral from negative infinity to t of x of tau d tau, that's the opposite of taking a derivative. So the Fourier transform of this should be 1 over I 2 pi f x of f. And indeed, this is true except for one catch. What about constant terms, which I'm going to call here DC bias, and we'll come back to that in a moment. So what about the f equals 0 part of this signal? Okay, notice that you can't divide by 0, right? So you sort of are losing something. So this formula here for the integral assumes something. It assumes that there is no so-called DC bias, or in other words, that the limit as t goes to negative infinity is 0. Okay, so as long as x starts off at 0 asymptotically in the negative direction, then this integral is nicely defined, and you'll have the property above. Okay, but if there's some constant term in x, then a constant term, as we'll see today, amounts to sort of a delta function at f equals 0 in frequency, and that's not going to be handled well. Another way to think about that is when you take a derivative, you lose the constant term. You can't get it back by integrating, right? And so notice that the f equals 0 part of the spectrum is gone. And the inverse is not going to get that back. Okay. Let's prove the derivative property because it's so simple. To prove this, we just say the derivative, let's replace x of t with its definition under the inverse Fourier transform. So this is the derivative of the, replace x of t with this formula. A df. Okay. Now, you say the derivative and integral can change places. So it's an integral. And we'll even take out x of f because that's constant with respect to t. The derivative does not affect that part. It's the derivative of the only part that depends on t. And that's a simple function to take a derivative of. So that's we just get an I 2 pi f. Let me put that in brackets. Okay. And now we just identify that this is the inverse Fourier transform of a new function. This whole function right here. Right? This is the inverse Fourier transform of that function. So and that's what our claim is. Our claim is that the Fourier, we've derived the inverse Fourier transform of this function is the derivative, therefore the other way is true as well. Okay? The Fourier transform of the derivative is this formula. So nice little trick. Now, we could look at another property for discrete time, because derivative property is only in continuous time. You only have derivatives in continuous time. But we could say, what about a discrete time difference property? So the closest thing to a derivative, how would you approximate a derivative in discrete time? What do you think? What's an approximation to the derivative in discrete time? Yeah. Great. So you're saying take a difference of two neighbors. I'm going to do it this way, but it really isn't going to matter much. Take the current one and the past one, or the future one and the current one. One of those is going to be a good approximation for the derivative, right? Okay, so let's see what happens. What's this Fourier transform? Now here, you really don't need a property. Linearity is all you need here, and time shift. So we know that this is going to go to x of f minus, and then a time-shifted x of f is going to be e to the negative I 2 pi f x of f, right? So that's the Fourier transform by linearity. I'm using the time shift property. Now, by the way, just to remember, a discrete time signal, its Fourier transform is always periodic. Okay, that's something we talked about last time. Conveniently, time shifts are always integers. So this will always, the result here is going to be periodic with period 1. You can just check these things in your mind. You know that it should be periodic with period 1. Indeed, if that's periodic with period 1, that is 2. This, because the time shift is always an integer, this here is periodic with period 1. So everything's still in good shape. Okay, I can factor it out. And I can use Euler's identity to write this as a sinusoid. Okay, how do I do that? This doesn't look like it matches up. Well, I'm going to factor out an e to the 1/2. So negative I 2 pi at times a half. That's just going to be pi f. Factor that out. And then what's left is e to the I pi f minus e to the negative I pi f. Now I'm starting to notice that's a sinusoid. Okay. So I'll do an extra step here. Right, there's that. So that's going to be I times 2 times e to the negative I pi f times sine of pi f, x of f. Okay, so there's a simplified version of it. Why did I do that simplification? Because I want to compare this difference property to the derivative property. Let me make a small comparison here. Notice that for small f, at least, we can approximate this quite well. For small f, this here, that right there, approximately equals 1. If f is small, that's approximately 1. Okay. This here, sine of pi f, if f is small, that approximately equals pi f. Okay. So that means that, what do we have? For small f, we have I 2 pi f times x of f. Isn't that exactly our derivative property? I 2 pi f x of f. So for small f, for small frequencies, this is basically the derivative property. In other words, if we don't have really high frequencies, then the differences are a great approximation to derivatives. Okay. If you do have high frequencies, frequencies near the sample rate, which is 1 for discrete time signals, then it's no longer a very good approximation. So in fact, to be a little more precise, the difference property applies, again, it multiplies x of f by some function, some scale, some amplification that depends on frequency. And that amplification is given by this formula, something like this. Oh, let me, right? In discrete time, we only care about frequencies up to a half because it's periodic. So we look at negative half to half. And then it would just repeat. Okay. And we have something that's a sinusoid times this function that's a constant and has a phase. Okay. So if we look at just like the let me just draw like a sinusoid. Sort of. Let's do that again. Okay, so that is what we're getting from the difference property. And it's near 0. It's approximately linear with a slope I to pi. Now that line, that would be the scaling that you would get from the derivative property. Okay, and so they're just close to each other near 0. All right, so I guess it would go opposite this way. Okay. So that's kind of nice comparison. Okay. So now we're going to take another look at the convolution property with a different explanation of it. This could have been a conversation that we had even before talking about the Fourier transform in general. And so this will give us just another way to kind of arrive at the convolution property. So imagine you have some system H, and you know it's LTI, which means all it does is convolution. Okay, now imagine that the input to this system is a simple complex exponential. We want to say, what does the LTI system do to a complex exponential input? Now, the reason we're looking at this input is because the complex exponential input is very special. It's a nice input for LTI systems in that it will always come out, the same signal will always come out just with a scaling. Okay, so there's a name for signals of this form. These would be called eigensignals. Okay, an eigen, like in linear algebra, an eigenvector is a vector that when you put it into your system, which is usually defined by a matrix, you get out the same vector scaled. Okay, and the eigenvectors are very important for understanding how the system behaves. So here, these aren't vectors, these are signals. But the signal, this signal, when you put it in, you just get it out scaled by A. A can be complex. Okay, and we'll figure out what A is in a minute. So this is actually true for all LTI systems. This is like a common feature of LTI systems. Okay, so let's both prove this and show that figure out what A is. Now A can depend on the particular eigensignal, so it depends on the frequency. Okay, so let's just do. All we know is convolution. Let's say plug it in. We know that y of t is the convolution of x of t with whatever our impulse response is of this system h of t. Now in this case. And convolution commutes, so I'm going to write it h of t convolved with x of t. Now in this case, we'll keep h of t general, but we'll plug in our choice of x of t, which was this complex exponential. Okay. Now let's do the convolution. Again, we're still keeping h general here. For any h, this is going to be true. So convolution is defined as this. I should replace t here with t minus tau. Tau, okay. And now I'm going to notice that I can split that exponential into a product, and one term in the product has t and no tau in it, so it can come out of the integral. The integral is this one here. There's a negative. Okay, so now I'm going to just identify that this integral no longer has t in it. So notice this thing is just a constant. For given f naught, this is just a number. And this is the so-called eigenvalue for that signal, because this is that A, right? Okay, so given a frequency, f naught, then we've just calculated, using only convolution, that we have some number, some integral, that's going to tell us how much that gets scaled. Okay. We could call this, we could label it, instead of using A, I'm going to call it capital H, because it depends, of course, on the system H. Depends on the impulse response H. It also depended on the particular frequency of our eigensignal there. All right? And, of course, hopefully somebody noticed something about this formula. Tell me, what is this H of f naught? Yes, so this is exactly the Fourier transform of the impulse response. Okay? Notice that we did not, we could have done this before talking at all about the Fourier transform. All you had to know was the definition of convolution here. And you had to know that LTI means convolution. And we would arrive at this formula, which happens to be the Fourier transform, but we wouldn't have to even know what it's called, right? Okay, so let's expound on this a little bit more. First of all, I want to give you another argument. Notice then, okay, complex exponentials are, or exponential functions in general, even real exponentials would work here, are special signals for LTI systems. They're the eigensignals. Now, we'd like to think of these as sinusoids, right? These are just kind of our generalization of sinusoids. And in fact, it's almost true to say the same thing about sinusoids. The sinusoids are the eigensignals. It's not quite true because a LTI system can cause delays. Okay, that's within the scope of what LTI systems can do. And if you delay a sinusoid, that's not the same as scaling a sinusoid. Okay? Complex exponentials are sort of nicer. If you delay a complex exponential, that is the same as scaling it by the phase. Okay? So, in some sense, this explains why do we go to the complex domain? Why do we use complex exponentials? Because they behave nicer than sinusoids. They're basically our sinusoids, but they have, for example, this property that shifting them is the same as scaling them. And that's why they become the eigensignals for LTI systems. Okay, so we can look at this in two different ways here. We could say, another justification or derivation of this is to think about what we know about the Fourier transform. That is, if x is a complex exponential, then its Fourier transform, right? The Fourier transform of a complex exponential is, we went over that last time. It's just the delta function at f naught. Okay, and since convolution in time is multiplication in frequency, then we know that the output is just yf times, it's just x of f times the Fourier transform of the system impulse response. And the delta function, then let's plug in our delta function for x. Then this is just a delta function times another function. Remember, we have a simplification. We don't need to keep track of that in the whole function h of f. We can just replace it with h evaluated at f naught. So let's keep our delta function there, and let's just evaluate h at f naught. So in other words, just the value at f naught matters. It's the only place where the delta function occurs. And now, basically, you see where this is going. It's saying that when you put a delta function in frequency, all that can happen to it is it can get rescaled. And that's why it's an eigensignal. Okay, you get rescaled by some number, h of f naught. I'll work backwards just to make that clear. Therefore, y of t equals the inverse Fourier transform of this thing. And since this h of f naught is just a particular number, then it comes out of the Fourier transform by linearity. H of f naught, Fourier transform of the delta function, inverse. And of course, we get back to our signal, h of f naught times e to the I 2 pi f naught t. So this is just another way to think about why are these the eigensignals, because they're delta functions in frequency. Okay, let's just look at what would happen. So we have this thing that's often referred to as a transfer function that I've written up above here. That this is, people call this h of f the transfer function of the system. It just tells you how the sinusoids or the complex exponentials get scaled. Okay, and it's equivalent to the convolution property, but it's just another way to come across it, and you call it a transfer function. Okay, so that means that if you actually put in a real signal, real sinusoid. All right. So let's say cosine of some frequency comes in here. You have some LTI system. It's got h. I'm going to just write h of f to describe it. And what comes out? And it's going to be, we've done this sort of calculation before. The magnitude of h is going to scale the cosine. And the phase of h is going to become a phase inside the cosine here, a phase offset. Okay, so you see, we usually, when we look at Fourier transforms, because they're complex, you have to choose how you want to interpret this complex function, and you have a choice. Usually the natural choice is either look at the real and imaginary parts of the function or look at the magnitude and phase. And now you can see why, in the frequency domain, it's very common to represent things magnitude and phase, okay? Because the magnitude has the effect of scaling your signal at that frequency, and the phase has the effect of shifting it in time or adjusting the phase. So it's just a nice representation. Okay, so let's talk about a DC component. A couple other names for this: DC offset, DC bias. These are all kind of related ideas, if not the same thing. So DC here is referring to direct current. Now, we're not doing anything with circuits and current right now, but it's just you borrow the idea of DC when you talk about signals to mean a constant part. Okay, so consider f equals 0 in our Fourier, both the Fourier series and the Fourier transform. Okay. So in the Fourier series, the f equals 0 term, really what we mean by that is the k equals 0 term. So we have coefficients, a sub k. Let's look at the 0th one, the a sub 0. Okay. If we look at what the formula says it equals, it's 1 over t integral over 1 period of x of t. Now, you normally, for the Fourier series, would have e to the negative I 2 pi k over t, t. Okay, but k is 0. So that whole thing is just 1. So for the 0th term, this is the calculation. That's the 0th term of the Fourier series. All right, and that's very intuitive to us. It's the integral. Well, it's the integral over 1 period. It's the average over 1 period. Because it's periodic, that's the average over the whole signal. Okay, so this is the average. All right, so the 0th term, this frequency 0 term, is the average in the Fourier series. And we would call that a DC offset. It's just the constant part that offsets this signal. Okay. Now let's go to the Fourier transform. Here we're not usually dealing with periodic signals, although we know that with the delta function, that's now within our capabilities to handle even periodic signals with the Fourier transform, right? But let's first just kind of think about non-periodic signals. What is x at frequency 0? Okay. Again, similar type of thing. Plug in the formula for the Fourier transform, but put f equals 0 in. That again kills the exponential term. So you just get this. So it's not an average, it's actually just the integral. Okay, remember, we're thinking about a non-periodic signal here. So this is just the integral of x. So instead of an offset, it might be more common to call this a DC component of your signal, okay? Because it's not like a constant offset. It's just the integral. Think of something that tapers off as you go to plus and minus infinity, but does have potentially a non-zero integral. Okay, so just to illustrate what we're talking about here, we have a Fourier transform that's a function that's has values for all f, and maybe it looks something like this. And we're just saying that the value of this Fourier transform at 0, there's x at 0. What is the meaning of that? The meaning of that is that's the integral of x. Okay. Now, what if we have delta functions? Then things are a little bit different. So consider delta function at f equals 0. Or let's also consider a delta function in time at t equals 0. Okay, so we'll just step away from the specifics of the DC component for a second and look at a couple of things. We already looked at what the Fourier transform of a delta function was at an arbitrary point in time, and the opposite. Let's look at it when it occurs at time 0. Okay, it's a special case. So delta of t. What's the Fourier transform of delta of t? What? Oh, you're saying e to the I f naught t. But f naught here, there's... e to the I f. Yes, but the t here is 0 in some sense. We could plug this right in, and we could say, well, this is the integral. So you could use the formula like you're using and just look at the special case. Yeah, exactly. And you'd get 1. Let me do it this way. Let's just directly plug in the Fourier transform. We say, and we use sifting to say, well, I should just plug into this function the value t equals 0. E to the negative I 2 pi f 0 equals 1. Okay, so that may seem a little bit odd. The Fourier transform of delta t is 1. Okay, but think of it this way. All frequencies are part of the delta function. So if you think about what the Fourier transform means, it means which frequencies need to be used to construct that signal. And the delta function has all frequencies equally. Okay? All of them are needed to make such a sharp spike. Okay, let's go backwards. Of course, by duality, then it's very clear that the Fourier transform of 1 is going to be delta of f. Yes? You're talking about doing this integral right here? Okay, but I think the critical point is you integrate at point 0, not 1. Let me just change your question, right? So you're saying from negative infinity to 0 and from 0 to infinity. Yeah. So because this delta function has an odd behavior, you want to avoid making the delta function occur at the edges, the limits of the integral. Remember that we have a definition for how the delta function behaves when it's multiplied by a continuous function. Okay? And when we put the edge of the integral at the same place as the delta function, technically that's like putting an indicator function inside the integral that chops off right at the delta function, right? And then it's discontinuous, and we don't have a good definition for what it does. Yeah. Good question. You were kind of constructing sort of a contradiction by saying you could integrate it that way. And yes, and this is the Dirac delta. In continuous time, we'll always be using the Dirac delta, which actually does have a non-zero measure for, even though its Lebesgue measure is 0. But yeah. Okay, so, but this is just the sifting property. So we know how to do this. And so what do I want to point out here? That the signal 1, what does that mean? That's a constant. Okay, that is a delta function at frequency 0. All right. Now, more interesting signals will have more than just a constant. So it might have a constant plus some other interesting signal. And in frequency, that would be like this. It would be like you would have maybe a variety of frequencies involved in your signal. So I'm going to draw the similar thing to above. But you also have a DC offset that is a delta function at time 0. Let's say it has height A. Okay, then this would be a DC offset of A. All right, it would be a delta function. Okay, let me try to fit something else in here. Oh, there's a nice the trick here. And that is that you can use this fact that the Fourier transform is related to the integral, that if you want to evaluate an integral, and you happen to know the Fourier transform, well then you don't have to do any work to evaluate the integral, because you would just say, oh, that's f at 0. If you knew what the Fourier transform was, just take its value at 0. Okay. Here's a similar type of thing. It's a different, it's another trick that's basically the same thing in another context, but it's just a nice example of how interpreting the special case of 0 can be useful. So sometimes if you continue signal processing beyond this course, you'll find that this so-called autocorrelation function is a useful thing to consider sometimes. This is the convolution of a signal x with its own time-reversed self. Okay, and there's a conjugate in there in case it's complex. So this is called autocorrelation. And notice something interesting. If you evaluate the autocorrelation at time t equals 0, then that is going to equal, in fact, the energy of the signal. And I'll just show you why that's true. It's just very similar to what we saw above. So the definition of R of t is this convolution, which we would write like this. X of tau, x conjugate of t minus, it's x of negative t there, so it's negative t minus tau. And a little bit of simplifying says that that's the integral of x of tau, x conjugate of tau minus t. And now we just plug in t equals 0, right? We want to know, this is a whole function. The autocorrelation function is a whole function, but if we just look at it at t equals 0, then what? It's the integral of x of tau, x conjugate of tau, which is magnitude squared, which means that's the energy. Okay, so just applying the same trick in another context. Okay, I do want to say one more thing. I know we're right about at the end of class time, but this won't take long. We looked at LTI systems in combination with all of the other properties like memoryless, causal, stable, and we said what becomes the condition for LTI systems. Well, I asked you to think about invertibility. I said by the end of the lecture, you might be able to know how to check if an LTI system is invertible because of the convolution property, in fact. Does anyone know how do you check whether an LTI system is invertible? So let's let h of f be the transfer function. In other words, the Fourier transform of the impulse response. Okay, I'm going to draw a transfer function here, and you tell me if it's invertible. Let's do that. Okay, so let's just say that's at least the magnitude of h of f. Do you think this is invertible? I hear some no's. Why would the answer be no? Yes, it maps exactly. Any part of your signal in this range becomes 0 in the output. You lose it. You have no idea what was there because it's a multiplication in frequency, right? So we lose parts of the signal. So it's interesting that if you check the transfer function, in other words, if you look in the Fourier transform of the impulse response, that's how you know if it's invertible. It's losing those frequencies. This part over here is the most significant part. This part over here would lose only maybe an isolated frequency, like a pure tone that exists forever is the only thing that you would lose here and not be able to recover, okay? Pure sinusoid. But over here, you're going to lose actual, signal. Okay, because that means that if h of f is not equal to 0 for all f, then it's invertible. And in fact, the inverse is simply going to be, the inverse will just be a transfer function that's the flip of it. So if you put it through a transfer function that's 1 over h of f in frequency, well, then that's going to recover any signal. So that will be its inverse. And you see if it's 0, you have a problem there. Okay, thanks.